Alrighty, hello everyone. Welcome to the Section 3 examples for the Abstract Modern Algebra lecture series. So we have 10 problems that we are going to work for this section. So let's begin working the problems. So for the first problem, we are asked to find the generators of the following cyclic groups. In U18, we are asked to find the generators of the subgroup 7, or the cyclic group of 7. And then for part B, we are asked to let G equal the cyclic group of A and the order of A equal 18. We're asked to list the generators for a subgroup of order 6. And then for part C, if A is a group element of infinite order, what is a generator of the intersection of cyclic groups AI and AJ intersection with the intersection of cyclic groups AM and AN? So let's start looking at these. So for part A, we have this group of 7 is the group of elements generated by 7. So let's figure out what those elements are. So 7 raised to the 1 is 7. 7 squared is 49, which is logically equivalent to 13 modulus 18. And then 7 cubed is logically equivalent to 1 modulus 18. So this group of 7 is equivalent to the set of elements 1, 7, and 13. So if you recall, in the lectures, we had one corollary that said the order of an element A is equal to the order of the group A, or the cyclic group of A, and this is from corollary 1 from our theorem and proof for the criterion that A raised to the I equals A raised to the J. So the generators of 7 will have an order of, well, we have 3 elements in 7, so the order of the group is going to be 3. So we obviously have that 7 equals 3. So we found that already. Then we have 1 is the identity, so we don't need to check it. So that only leaves us with 13 to check. So 13 raised to the 1 is 13. 13 squared is 169, which is logically equivalent to 7 modulus 18. And then 13 cubed is logically equivalent to 1 modulus 18. So the order of 13 is 3. So 7 and 13 are generators of 7, or the cyclic group of 7. All right. Let's go to part B. So for part B, we're going to look at another corollary that we mentioned. So if you recall, we had one corollary that stated in a finite cyclic group, the order of an element divides the order of the group. And this was from our proof that cyclic group AK is equal to the cyclic group of A, greatest common divisor of N and K, and the order of AK equals N over greatest common divisor N and K. And this was the first corollary from that theorem. So, let's see here. So, the subgroup is 18 divided by 6 equals 3. So the elements are of the subgroup A3. So A3 is a subgroup of G, and the elements are E, A3, A6, A9, A12, A15. And the generators and if we go back to another corollary 3 of the same proof, the greatest common divisor, K and 6, needs to be 1, and A3, A9, A15, these all have the greatest common divisor of 1, so the generators are A3, A9, A15. Okay, so I'm going to go to the end of my notes here because I didn't space these problems out enough so we can do part C. So I'm going to put continued at bottom of page for these notes. And then we'll scroll all the way down here. Put a big space in between these problems. All right, and then we will continue right here. So for part C, we're going to be doing something similar to B. I'm going to put problem 1 continued. So we have the intersection of these groups. Well, we're going to use a corollary to reason out that this is equal to the subgroup of the least common multiple of these elements. And then same can be said for these two. And then we will have the least common multiple of I and j intersection least common multiple of m and n, and that is going to be equal to the least common multiple of I, j, m, and n. So a generator is a raised to the least common multiple of I, j, m, and n. And we are done with this first problem. Alrighty, hey everyone, welcome back. So I got problem one fixed and spaced out the problems more. So I've got this text combined with problem one. So now we are done with that problem. Let's move on to problem two. So we have let G be a cyclic group and H be a subgroup of G with an element H. And we're asked to prove that the order of H divides the order of G and H is cyclic. Okay, so this is going to be real similar to when we proved the theorem of the fundamental theorem of cyclic groups. So we will use a similar proof to that. So we're going to let G be equal to H and H be a subgroup of G. We put where H is an element of H and H is a subgroup of G. So let's assume that H does not have just the identity element in it. So then HT is an element of H, where T is greater than 0. So since G is cyclic, every element H has the form H of T, and when H of T is an element of H, with T less than 0, then H negative T is an element of H with negative T greater than 0. Now let M be the least positive integer such that H of M is an element of H. So thus the cyclic group of H of M is a subset of H by closure. So now let's suppose that H equals the cyclic group of HM, and let B be an arbitrary member of H. So then B is an element of G, which is equal to H. So B equals H raised to the K for some integer K. So then there exist integers Q and R such that K equals MQ plus R, where 0 is less than or equal to R is less than M. So hence H of K equals HMQ plus R, which equals HMQ HR, and whence HR equals H negative MQ HK. And since HK is an element of, or equals B element H, and H negative MQ equals H M negative Q, which is an element of H. HR is an element of H. Or then HR is an element of H. There we go. However, M is the least positive integer such that H of M is an element of H, and 0 is less than or equal to R, which is less than M. So R equals 0, and thus B equals HK equals HMQ equals HMQ, which is an element of our cyclic group of H of M. So therefore, the order of the cyclic group H of M defies the order of the cyclic group of H, where the cyclic group of H equals G, and H is cyclic as desired. So yeah, that proof was a lot to consider, but we're basically are just following the proof for the fundamental thermocyclic roots. We're just changing our variables based on our problem statement. All right, let's go to problem 3. This is an interesting problem. So we are asked to list all the elements of order 15 in Z 150. Let's see, that's 9 zeros. So it's 1.5 times 10 to the 8th. 1, 2, 3, 4, 5, 6. Yeah, to the 8th. I can't, it's somewhere in it's I don't know what I know billion is when or this is in the millions, yeah. But we're asked to let A be a group element such that the order of A equals that big number. So we need to list the elements of order 15 in the cyclic group of A. I think 100 million is the right word for this. 150, 100 million or something like that. I'm kind of a little dry on those words. I haven't described a big number like that in a while. Well, let's take a look at this one. Might post a comment down below when I figure out the name of this. So the order of this group is going to be, so corollary 1 from our second proof in lectures will be used. So we're going to let K be an element of this group. So then the order of K divides the order of this group. Or elements K are all the elements where this big number divided by the greatest common divisor of K and the big number are 15. So this big number divided by 15 equals 10 million. We won't include the commas, just 10, 10 million. So 150 million, that's the number. Don't know why I was being bad at remembering that. And also the elements are K equals 10 million times J, where greatest common divisor of J and 15 equals 1. Well, this is just simply going to be the elements of this group. 1, 2, 4, 7, 8, 11, 13. So the elements are 10 million. We'll write this as a set. 10 million, 20 million, 40 million, 70 million, 80 million, 110 million, and 130 million. And this is the first part of this problem statement done. So the second part for the group element A, where order of A is 150 million, we will have the same elements in the form A raised to the K. So our elements are going to be a 10 million, a 20 million, a 40 million, a 70 million, a 80 million, a 110 million, and a 130 million. And that is it for this problem. Let me see if I can box this answer too. All right, that is it for problem 3. Let's go to problem 4. So we have for the set 7, 14, 21, and 28, we need to construct a Cayley table to show the set is a group under multiplication modulo 35, and we need to determine if the group is cyclic and what its generators are. So the solution, let's construct the Cayley table first. And our operation is going to be multiplication modulo 35. So we have 7, 14, 21, 28, 7, 14, 21, 28. Then these are the elements we will get when we multiply them. 7, 21, 21, 14, 7, 14, 21, 8, 7, 28. So the way this Cayley table works is when you multiply 7 by 7, you get 49, and that's logically equivalent to 14 modulus 35. So if you were just wondering where these numbers are coming from. So to be a group, we need to check the properties of a group. So it needs to be associative, and just by nature, we're doing a multiplication group operation, and that is associative. Then we need to have an identity, which is when an element multiplied with another produces the element. And if we look at our table up here, we can see when we multiply 21 with all of our elements, when we multiply it with 7, it gives us 7. When we multiply it with 14, it gives us 14. 21, 21, 28, 28, so on and so forth. So 21 is our identity. 21. So we have identities, and then we need to check for inverses. So every element must have an inverse. So for 7, we have 7 times 21 equals 7. So we need an element that gives 21. So 7 times 28 equals 21. So the inverse of 7 is 28. And then for 14, we have 14 times 14 equals 21. So 14 inverse is 14. And then 21, well, that's our identity. So 21 inverse is going to give us 21. And then 28 is, we can see from 7 that 28 inverse is 7. So therefore, the set 7, 14, 21, 28 with multiplication modulo 35 is a group. All right, so now we know that it's a group. Now we need to determine if it's a cyclic group. And to do that, we just need to find if we have generators in this group. So we need to test for generators. So 7, 1 gives us 7. 7 squared is logical equivalent to 14 modulus 35. 7 cubed is logically equivalent to 28 modulus 35. And 7 4 is logically equivalent to 21 modulus 35. And this means that 7 is a generator. So the group is cyclic. Oops. Let's do check mark. And then we need to find the other generators. Well, I will leave that if you want to do that on your own time, but by testing more, we will find that 7 and 28 are generators. And this problem is done. Trying to make my diamond a little more straight. Alrighty. Yep. That is it for problem 4. So now we will move on to problem 5. For problem 5, we are asked to prove that for any prime p and positive integer n, that phi of p raised to the n equals pn minus pn raised to the n minus 1. So let's write out a proof strategy for how we're going to prove this. So we can directly prove this by showing that p raised to the n minus 1 is all the numbers that are not prime to n, and therefore subtracting it from p raised to the n gives us the non-negative integers less than n equals pn that are prime to n. And this is accomplished by defining p raised to the n and p as sets and showing that p raised to the n over p is the set of numbers not prime to n. All right, so let's write out our proof. So we are going to let p be a prime number and n be a positive integer. we need to define, or let's define A as the set 0, 1, 2, so on and so forth, up to p n minus 1 as the set of non-negative integers less than p raised to the n. So then the order of A is Pn. And now let's define B as the set 0, P, 2P, so on and so forth, as the multiples of P. So then the order of B is P. So hence the order of A divided by the order of B equals Pn over P equals P to the n minus 1. So a set of non-negative integers not prime 2 n has order p n minus 1. So therefore, phi of Pn equals p raised to the n minus p to the n minus 1 represents the number of non-negative integers less than n equals Pn as desired. All right. All right, that is it for problem 5. Let's take a look at problem 6. So we are asked to find the number of elements that A have order 4 in a cyclic group of order 64, and B have order 50 in a cyclic group of order 750. So we can continue on what we just covered in the proof of problem 5 for this. So we need to check if 4 divides 64, and if it does, we can use the theorem we proved in the lecture. This was the 4th theorem that we covered. Which was about number of elements of each order in a cyclic group. So 4 does divide 64 because that gives us 16. So then we have phi of 4. Well, that's equal to phi of 2 squared. We can write that as 2 squared minus 2 equals 2 elements. And then for part B, well, we have 50 does divide 750 because it gives us 15. So then phi of 50 equals phi 25 and phi, or times phi of 2, which is equal to phi 5 squared times phi of 2. So we will have 5 squared times 1, and that's equal to 25 minus 5 times 1 is, and that gives us, here, we'll put it down here, equals 20 elements. All right, and that is it for problem 6. Now let's move on to problem 7. So we are asked to prove that for a positive integer n, that a cyclic group of order n cubed plus 6n squared minus 32 has n squared plus 7n plus 12 elements of order n squared plus 8n plus 16. Let me see if I can fix that to line up. There we go. So this is going to be continuing off of the finding the number of elements of each order in a cyclic group. So let's start by doing some scratch work. So let's show that this polynomial divides this one. Of course, we'll have to add a 0 in because we don't have an n term. All right, so we will first multiply by n. And that gives us negative 2n squared, negative 16n minus 32, and then we will need to multiply by negative 2. And that gives us 0. So yes, this does divide our cyclic group. The order of this group divides the order of this one with no remainders. So n squared plus 8n plus 16, and then divides n cubed plus 6n squared minus 32, and n squared plus 8 n plus 16 factors out to n plus 4 squared. And this will be useful when we write out our proof to prove that we have this number of elements in this cyclic group. So let's begin writing our proof. Let's get my pen here. Write a proof. So let's let n be a positive integer. And let a cyclic group have an order of n cubed plus 6n squared minus 32. So then we have n cubed plus 6n squared minus 32 equals n squared plus 8n plus 16 times n minus 2. And so squared plus 8n plus 16 divides n cubed plus 6n squared minus 32. So hence phi of n squared plus 8n plus 16 equals phi of n plus 4 squared, and that is equal to n squared plus 8n 16 minus n plus 4, and that gives us n squared plus 7n plus 12. So therefore the cyclic group has n squared plus 7n plus 12 elements of order n squared plus 8n plus 16 as desired. All right, that is it for problem 7. All right, so for problem 8, we are asked to determine the subgroup lattice for Z24 and generalize it to the form Z p cubed Q, where P and Q are distinct primes. Well, let's take a look at this. So, a subgroup lattice. What is a subgroup lattice? Well, we'll look at what that is in a minute, but it's kind of like a little chart of the subgroups that make up a group. So, let's figure out what the subgroups are for Z24. So, the first thing we need to do is we need to identify the divisors of 24, and those are 1, 2, 3, 4, 6, 8, 12, and 24. And these can all generate subgroups based on their order. So recall that for a cyclic group of A, the order was equal to n over greatest common divisor of n and k. So let's take a look at all these divisors and see what kind of subgroups we get. So 1, that is the identity. So it will just be the cyclic group 0. For 2, we have 24 over greatest common divisor of 24 and 2, which is equal to 24 over 2 is 12. So this will be cyclic group of 12. And then for the rest of these, I'll just write out what their subgroups are, because from seeing what we did with 2, I think you can understand how we figure out what these are. 6, 8, and then 12. So let's build our subgroup lattice. So the way the subgroup lattice works is, if you notice, all these subgroups, at least from 12 to 2, they're all subgroups of each other. So we need to start with our identity 0, and then from our identity we can branch off into these subgroups. So we will have 2 subgroups of 12 and 2 subgroups of 8. And then for 12, we can split it up into the subgroup 6 and the subgroup of 2. Then 8 can be 4, which is also a subgroup of 2. 12, subgroup of 6, but 6 can also be split up or divided by 3. You know, that's kind of a trick for this particular problem with these subgroups, is they're all divisors of each other. And that can be split up to 4. And then 1 is going to define our entire group Z of 24. So all of these are subgroups of our main group. And this is our subgroup lattice. Sorry, I went over the 0. Let me see if I can fix that. So, and did that automatically. See maybe if it'll get it this time. There we go. All right, so for Z P cubed Q, we will have subgroups P squared, P p cubed, q, pq, p squared q, and then of course we will have 1, our group, and then our identity 0. So our new lattice is start with our identity, and we can branch off this way. We'll start with p cubed, p squared, p, and then if we go down here we can start with p squared q, and then p q, q, and then this will all go back to our group. And the reason that we can generalize this in the form z, p cubed, and q is, remember, our problem statement said that p and q are distinct primes. So out of these divisors of 24, we'll let 2 and 3 be our primes, because out of these divisors, of course 1 itself is also prime, but it's also our identity. 2 and 3 will be our divisors. And we can, these forms can represent basically all of our elements we have in this subgroup lattice. So if we let p be 2 and q be 3, well, p cubed is 8, p squared is 4, p is 2, and then p squared q, that's 12, because that's 4 times, well, 2 times 2 times 3, 4 times 3, and then pq is 6, 2 times 3, q is 3, and then 0 is 24. So that's the reason we can generalize this group into this subgroup lattice. And compared to the lattice we had before, this one is a little bit simpler. All right, let's look at problem 9. So for problem 9, we are asked to prove that a group with prime order must be cyclic. Well, this is going to be a pretty straightforward proof, so I'm not going to worry about writing out a proof strategy explaining what we'll do. So we are going to let G be a group and the order of G be prime. Let's define E as the identity of G. So then there exists an element G in G where G does not equal the identity element. So let's consider the subgroup, the cyclic group of G. So then the order of the cyclic group of G divides the order of G. If you remember, that was one of the things we covered in our theorems in the lectures. So since G does not equal the identity element, the order of this cyclic group cannot be 1. Yeah, the order of the cyclic group cannot equal 1. So thus the order of the cyclic group G equals the order of G. So therefore G is cyclic as desired. And the reason that this works is because for our cyclic group of G, since the order of G does not equal 1, it has to equal the order of G because the order of G is prime. And prime, it's either 1 or it's either has divisors of 1 or itself. All right, that's it for problem 9. Let's look at the last problem, problem 10. So we are asked to suppose that the order of A equals n. So what condition is required to satisfy that the cyclic group AI is a subset of the cyclic group AJ for some I and j? All right, let's take a look at this. So if you recall from a theorem, we have the order of AK equals n over greatest common divisor of n and k. So we have the order of AI equals n over greatest common divisor of n and I, and the order of AJ equals n over greatest common divisor of n and j. So for the cyclic group of AI to be a subset of the cyclic group of AJ, AI must equal AJ raised to the m, where m is an integer. So n over greatest common divisor of n and I must divide n over greatest common divisor of n and j. So by divisibility, we can rearrange to get a new condition. Try to fix that W. There we go, a new condition. So we have n over greatest common divisor n and I divides n over greatest common divisor n and j. Well, we can treat this like n over greatest common divisor n and I equals n over greatest common divisor of n and j. So what we can do with that is we can multiply everything on the other sides and the ends will cancel out. And once we do that, this will give us that the greatest common divisor of n and I, or n and j, excuse me, n and j divides the greatest common divisor of n and I. So a required condition is greatest common divisor of n and I must divide greatest common divisor of n I keep getting this mixed up. And a J and an I. There we go. So we can write this as cyclic group of AI is a subset of cyclic group of AJ, and we can define this as a biconditional if and only if greatest common divisor of N and J divides greatest common divisor of N and I. And that is it for problem 10. Let me try to get a better diamond symbol drawn. Guess that's as good as I can get it. Let me double check. I don't know if I put one with problem 8 up here. Okay, I did. Good. All right. Well, hey guys, that is it for the section 3 examples for abstract modern algebra. Thank you guys so much for watching, and there will be a bonus lecture for some programs for finding generators of cyclic groups if you're interested in watching that. So, hope you guys enjoyed. Please leave a like and comment if you have any thoughts. Thank you.